All right, tell me the steps. Step 1, read the problem. Step 2, draw the picture. Step 3, list what we know. And this is not grammatically correct, but I'm going to say list the knows. So we'll say knows, right? And then 4, what do we do?
Need to know.
List the need to knows. And again, that's not grammatically correct. It's just little s. On number 5, what do we do next?
Equation.
Equation. We know it. You don't have to write it down. Oh, really?
Solve.
And number 6 is solve. So that's the process. So now we're going to do problem number 37. Problem number 37, let me read it out loud. It says a 60-kilogram astronaut floating at rest in space outside of a space capsule throws his 0.5-kilogram hammer such that it moves with a speed, not a velocity, but a speed of 5 meters per second relative to the capsule. What happens to the astronaut? No, it doesn't. Now on Earth, if you throw something, when I throw this, it just goes. You know why?
Gravity.
Gravity is holding me in place. So since gravity is holding me in place, when I throw it, you know, technically for momentum to be conserved, I should kind of float back a little bit. But he's in space. So we draw the picture. We've read it. Now let's draw the picture. Here's my little space capsule.
That looks like a speed gun.
Have you ever been on a space capsule? Huh? It's the best I can do. I'm a math/physics teacher. And so we got this, because I'm going to do a stick figure for the, before you criticize me, I'm going to do an astronaut as a stick figure. So he's out there, all right?
Where's his suit? Yeah, how's he not going to float away?
He's a stick figure. He doesn't need a suit.
Don't they need those?
But I am going to give him a helmet.
Everyone needs a suit. They need those.
What the?
hose.
That's his voice.
Exactly.
Looks like a pimple.
From SpongeBob.
So now he has a mass. So we draw the picture, right? And he has a hammer, right? And this is the hammer that he's going to throw.
Yeah.
He has a hammer, and he's going to throw it this way. Now that's the picture, right? He's got a hammer in his hand. He's standing in space, and he's going to throw the hammer. Now they're saying that they're relative to the space capsule. What they mean by that when they say it that way is we know that the space capsule is moving, but he's not moving relative to the space capsule. And the hammer is not moving relative to the frame of reference of the space capsule. Okay? And so let's read that again. It says that, so now what do we need to list? We drew the picture, now what? Now I need to list the notes. So I'm going to read it again. And it says that a 60 kilogram, that's his mass, right? 60 kilogram astronaut is floating at rest in space at rest. What does that mean about his velocity? 0. So his initial velocity, and I'm going to do some subset notation. I'm going to say sub A O. That means the velocity of the astronaut, and then the O is the initial part, right? Is 0 meters per second. And then he has a hammer, and it says that his hammer, and let's make the hammer a different color so we can kind of see what's going on. His hammer has a mass of 0.5 kilograms. And he's going to throw it such that, okay, so what is the initial velocity of the hammer? He has it, and he's going to throw it. But before he throws it, what is it? 0. So the velocity of the hammer, the initial velocity of the hammer is 0 meters per second. And then he throws it. So when he throws it, he will have created a velocity in the hammer of 10 meters per second. That's what the book says, right? Okay. Now what it says is, what happens to the astronaut? That's the question the book asks. So we listed what we need to know. The book says, what happens to the astronaut? In fact, let me read it exactly how they word it. What happens to the astronaut? Well, okay, that's exactly that. So now, we have listed what we know. We have listed what we need to know. Now we got to find an equation of some sort. Now, when you look at the information there, what are we talking about?
An astronaut.
Velocity, the velocity of the astronaut, and we know because we're talking about the conservation of momentum, we know a couple of things. So just to kind of go through the thought process I think that you guys will go through at home, we might say something like, all right, I know that the momentum, right, of an object is equal to the mass times the velocity. I know that momentum, well, I'm just going to use P. We know that the momentum is conserved. Now somebody said we want to look at the final velocity of the astronaut. Who said that and why did you think that? I mean, you did the answer and got it in the back of the book, but who said that? Oh, now nobody wants to say it. Did you say it? Why do you think that? When we look at that, it should be kind of intuitive. What do we know? Yeah, when we look at this, we have all the information for the initial total momentum, and we have almost all the information for the final momentum, except one thing. What are we missing? The velocity of the astronaut, right? So now, how do I do that? How do I do that on the board? Well, let's list some things. If I wanted to, I have my initial momentum, and the initial momentum. So what we're looking for. Let's write it like this. What is wrong with this thing? Okay, now it's working. What I'm looking for is the initial momentum of the total momentum of the system, right? So I'm looking for the momentum of the astronaut, the initial, plus the momentum of the hammer and the initial. Now, what do I know about the initial momentum? The sum of those. It should equal the final momentums, right? The final momentum of the astronaut plus the momentum of the hammer. Is that right? Okay, now watch this. So that means I have the mass of the astronaut times the initial velocity of the astronaut plus the momentum, right, or the mass of the hammer times the velocity of the hammer, the initial velocity. That should be equal to the mass of the astronaut, right, times the velocity of the astronaut final, plus the mass of the hammer times the velocity of the hammer, the final, right? And we know all this information. And we know all of them except that, right? Is that right? Now, to save time and skip some steps, if I solve for this, well, actually, let's just plug the numbers in. I'm going to do it a little bit different. So what's the mass of the astronaut? 50 kilograms times, what's his initial velocity?
He's 60 kilograms.
He's 60 kilograms? Now, what's his initial velocity, though? 0. All right, plus 0.5 times 0. Hey, that makes it a lot easier, doesn't it? We're going to end up with 0 here. Okay? Now, over here on this side, I have the mass of the astronaut, which is 60 kilograms. I don't know what this is, right? Well, I do know what this is. What's this? This is going to be 0.5 times the final velocity, which is 10, right?
Yeah.
So I've got 60 V, that's not a V, V, A sub F, and then half of 5 is 10, right? Or half of 10 is 5. Is that right so far?
Yep.
All right, so now I'm going to move the 5 over to the other side, and I get negative 5 is equal to 60 VAF, right? What should I do next? Divide by 60. And somebody on your do that on your calculator real quick and tell me what you end up with.
0.083.
Yeah, so it should be something like 0.083,
Yep.
right? And that is the final velocity. And it's meters per second. I ran out of room. Any questions on that? Now, what is that saying?
He goes that speed in the other direction.
Yeah, it says that once he throws the hammer, the astronaut will move in the negative direction with a final velocity of 0.083 meters per second. So when he throws that back, he'll start to drift back a little bit. Does that make sense? Okay. Any questions? Does that make sense? Are there any questions? No? Good.